Okay, so in general, if we want to understand the long-term behavior of the chain, then it will be helpful to identify and calculate the marginal distribution of xn. More precisely, we want to examine the probability that a Markov chain is in a specific state x at time n, given it started with an initial distribution mu. The theorem on this slide illustrates how to calculate the marginal probability of a Markov chain started in a particular state. This is very, very mathy, and I know that we all come from different mathematical backgrounds, but fear not. This is for those of you who really just want to look underneath the hood. We're going to be able to go through a bit more of an applied version of this in just a few slides. But here's the theory. So let's take a look at this corollary. All right, so for any initial distribution mu, the probability of xn equal to x is the x position of mu transpose times p to the nth degree. The proof is shown. This corollary is an immediate consequence of the proposition from the previous slide, which is actually also the following slide. For each n element of the natural numbers, the matrix p to the nth, which is p times p times p times p, and times, is stochastic. Furthermore, for each n, the probability at time x of xn being equal to y is equal to the probability of xn being equal to y, given that x naught is equal to x, which is equal to, which can be found in the x, yth position in the p matrix to the nth degree. So if you multiply the p matrix n times, then by itself n times, then you could take that result and find the xy position in the result, and then you could see, oh, that would be the probability. So, okay, in other words, this is saying that for a time homogeneous Markov chain xn, the marginal distribution of the chain given at time n, given that it started at state x, is equal to the probability of xn being equal to y, given that x naught equals x, and we can find this at the xy position of the p matrix to the nth order, which is just restating what I said. Okay. Similarly, if the chain starts according to a probability distribution mu on state space S, then the marginal distribution of the chain at time n, given that it started at state mu, is given by the probability that xn equals y, given that x naught follows mu, is equal to the yth index of the product of mu transpose times p to the n. Okay? The following proposition is known as the Chapman-Kolmogorov equations. I don't know if I said it correctly. So you can kind of just read that. And the proof, you can read through that as well, follows from the time homogeneity and Markov's property. Okay, now, so this finally brings us to a practical example application of the things we've learned today. I didn't feel like we can come here without going through all the things that got us to here, for example. Suppose we've been given this following problem. Let the set of xn be the Markov chain with state space S being equal to the set of 1, 2, 3, 4, and a transition matrix P, which we've been given here. Note that we've also been given an initial distribution of mu transpose, all right? You can see that in the middle. And we want to calculate the following problems, all right? 1, 2, and 3. For the first problem, we want to find out what the probability that x sub 5 equals 3, given that x3 equals 2, okay? So recall from our first proposition that we can plug in for this formula, right? So for our first problem, we just need to solve for the p matrix squared and identify the value at the second and third position, the 2, 3 position. As you can see, it might be kind of annoying to have to square this p matrix by hand, right? So for our second problem, we can use this property from the Chapman-Kolmogorov equations that we just saw, to plug in our values for n equals 3 and y equals 2, since we want the probability of being at this value of 2 at our third step. Okay? So you can see we need to solve mu transpose times the P matrix cubed and identify the position at y equals 3. Okay? So this third problem will be more complex because it involves a sequence of transitions. So it can be computed using the chain of rule for probabilities, and it involves multiple transitions. So here, we will need to compute the probability under an assumed mu distribution of x8 being equal to 1, given x6 is equal to 2, times the probability that x6 is equal to 2, given that x3 is equal to 2, times the probability of x3 being equal to 2. So this requires us to calculate these values right here, according to the previous propositions, and then we will multiply the values together. So we can do all this in R, thank goodness, because that would be really annoying to have to multiply that many matrices together. We can identify the values at specific indices as well pretty easily. So here you can see that I've created the P matrix at the top here, the mu transpose vector, and I've calculated and stored the values of P squared and P cubed. For problem 1, I can just reference the values sitting at the position x equals 2, y equals 3 of the squared P matrix, and there we can we get the first result is 0.09375. For problem 2, we multiplied the mu transpose vector to the cubed P matrix, and we retrieved the second element, which is found to be about 0.3577. And in problem 3, we call the indices to the squared and cubed P matrix associated with the respective probabilities for x8 equals 1 given x6 is equal to 2, and for x6 equal to 2 given x3 equals to 2. So, and we multiply it for the probability of x3 being equal to 2. So finally we have a solution for number 3 as being 0.02835.